So we'll start with a basic problem, which is kind of identifying people and where they are in an image, tracking them through multiple image sequences. Then we'll go and talk about improving accuracy. So the approaches I'll start with are kind of these really classical approaches that have been done for about 20, 30 years. But more recently, there's been a lot of advancements in neural networks, which I'll talk about in detail in the second half. And then I'll talk about what's next, because there's some really interesting research going on all the time in image recognition. When I was running this project, a new technique came out that literally as we were in sort of like the second week, where we were like, we want to use that technique. We want to use their models and their stuff from their paper. So, and even since I put this presentation together, there's been some stuff that I'll touch on at the end. So we'll start with the finding people problem. And if you take a grocery store, kind of, I guess, guesses what the project was on, we want to count the number of people who enter into that grocery store. And what you might have is, in a frame, you want to draw some useful information around. So the image on the right, you'll notice there's a green outline around that person just entering the door. That's useful information for you if you want to count them or track the number of people, see where they hang around in the store, and maybe even observe, how long they spend in the store and that kind of behavior. So the process we'll go with is really simple, and it's just called background subtraction with contouring. Background subtraction is literally the process of kind of averaging lots of images and figuring out what the base background is, and then just taking that background away from another image. So a quick example of how to do that would be using NumPy pandas and OpenCV. OpenCV is called Open Computer Vision, and it's a really big library for doing many different kinds of image operation. It's quite weighty, and there are more efficient ones for other things, but OpenCV covers lots of bases with the kind of capabilities it has in it. So if you imagine, what we might do is we might have this kind of empty store, which is our background subtractor, which is our background, and we initialize a subtractor, and we take away kind of the current frame of a video from it. And you end up with this ghostly image on the right, which is basically kind of the pixel difference between the empty store and the store with somebody in it. And it's nothing more than that. It doesn't tell you that this is a person. It doesn't tell you that there's some, a dog or a cat or some items in the shop. And you'll notice that it's particularly noisy as well. Images from video are inherently noisy. They contain things like heat distortions from, say, a refrigerator emitting heat will cause these kind of pixel values to change. So you just end up, when you take one image away from another, you end up with some inherent noise in there. But there's probably enough information in that image to at least recognize there's two people at least. And that's kind of the information that we need to make progress. As I said, the result's messy. And there's even some kind of weird computer screen thing on the left that we don't care about. What we can do is we can do a process called opening, which if you imagine, it's kind of like sieving, where you effectively you just lose pixels that are really small and on their own, and and what that results in is you kind of remove a lot of the noise, but you also take away a little bit of the edges of some of the big shapes. That process is really useful because what you don't want is lots of noise in your image. You want large, usually you want kind of large approximations of where people are. And again, this is a really old technique. This isn't like something new or particularly interesting. This is just something that's very tried and tested and used kind of a lot in the security industry for motion activated security cameras and that kind of thing. The other part is basically combining the same two processes that we used on the other side of opening, but doing it the other way around, and the sieve metaphor kind of doesn't work that way around. But effectively, if you look at the image on the left, you'll see that, say, it's got a lot of thin and kind of wispy detail around the woman's arms. And on the image on the right, what's happened is it's actually kind of filled in some of those wispy details around the neckline and the other image. And what that's done is it's just resulted in again, a more cohesive shape, because what I'm really after is a blob that the computer can draw around rather than something with holes and fuzzy edges. We can do it again with kind of changing the size of the coarsity of the sieve effectively, and that just results in a slightly different case. Now, if I was going to spend loads of time on this, I'd work on it until I didn't have any noise, because you can see the last process has brought through a lot of noise. But that's kind of an example of when you don't necessarily do it quite right. In a really well-tuned example with a really well-initiated background subtractor, the background subtractor has to be something you average over time, and it's kind of quite a manual process to get it set up. You could eventually, how you construct that background subtractor can have a large impact on what this ends up looking like. So effectively, the process that happened kind of 3 or 4 slides ago was very kind of just rudimentary at best. And when if you were doing this properly in a production scenario, or in a more commercial scenario, you would spend a lot more time working on that initial background subtractor and all of the conditions around getting it set up. So we're going to move on, and eventually we end up with this kind of shape. And from there, what you can say is just draw polygons around the largest shapes for me. So from there, you can end up with a nice draw image of a green line around the interesting shapes of the person by the door. So by those simple bits of maths of taking one image away from another and doing some various processing to reduce the grains of sand and maybe make sure you've got a singular large blob, you can end up with the useful information I was talking about on the 3rd slide. So that's the real basics of tracking somebody or finding somebody in a singular image. And you can generalize it by effectively doing multiple frames, and then just kind of doing some basic vector tracking, which of where those polygons go from one frame to another. Again, very straightforward, and prone to errors as well. So really prone to errors when 2 people overlap, quite obvious, because what happens is the process ends up making a really large blob instead of 2 distinct blobs. So you have to have some quite careful logic in there around making sure that you don't suddenly turn 2 people into 1 and then 1 into 2 again, which can very easily happen with this approach. But if you have enough cameras in the right places, it's perfectly adequate to get you where you need to go. But the problem is it doesn't actually tell you anything about the type of thing that it's seeing. So you don't know whether a large blob is a person or a shadow or a car. You can't tell the difference between a car and a person, which is a really common use case or common scenario. What you really want is something that looks like this, where each individual thing is actually recognized and localized on the image, and then labeled with the class that it thinks it is. So in this case, it's recognized the tie and the umbrellas and people, and it's recognized them in situations where there's occlusion. So on the left-hand side, where the shoulder is basically occluding most of the person's body, it's recognizing the umbrella even though it's misty. There's no way you could get to this with the subtraction I talked about before. This is something a class entirely different. So there are a few different classes of problems. These are kind of the ones I'll focus on for now. There's the classification, which is literally just showing it an image and just saying there's a hot dog in it. There's identifying where on that image the hot dog is. There's drawing a polygon around where you think or drawing a square around the multiple objects within the same image. So rather than just choosing the best, the most obvious class in that image, you actually draw all the different types of things. That's generally classed as a detection problem. And then there's the drawing polygons around stuff. Now the instant segmentation part, that's one of the kind of holy grail stuff of self-driving car technology, and it's actually a really slow process. So to do this can actually run at about 60 to 90 frames a second on a Titan X GPU, which is kind of the latest graphics card from NVIDIA. And that basically means it's real time and faster than humans can do at an 80% accuracy. But for the segmentation problem, which is inherently useful for some of those self-driving technologies, this process is really slow. I think you're talking about I think it's 1.6 frames per second is the very best that you can get at the moment, which is just really choppy, obviously, for humans to see, and that's kind of one of the kind of main just processing power is kind of holding back a load of use cases, and when that happens, and also the techniques are holding back some of the use cases you could do if you could draw around different types of objects. Because then if you could do that, you could have things like mid-air interception of objects by a computer. Whereas if you're only getting 1.6 frames a second of image segmentation, drawing polygons around an image, you're never going to be able to have a machine intercept something in real time really accurately. You can get that pretty close, but you're not going to get that real high precision accuracy. And this section is all about accuracy. So I'm going to talk about how you measure accuracy. Principally, how many people are comfortable with precision and recall? Hands up for precision and recall. Okay, yeah. So precision is like how often do you say something is a hot dog? You're usually right about it, and the recall is can you identify most of the hot dogs in the population? So they measure different metrics. One of the metrics that's commonly used is an F2 score. So a lot of people are familiar with F1. An F2 score is basically the harmonic mean of kind of like the derivative of the F1 score, and what it does is it weights precision more highly than recall, which for image classification problems is usually a preferred thing, because actually if you have a little bit of error in your if you have more error in your precision, it's generally seen by humans as worse in these kind of scenarios. So F2 kind of relates more to just the way humans perceive something to be good in this scenario. But the problem with these is they're really, really good for judging classification problems, but they don't tell you when shapes overlap or how accurate you are with your localization. So a really common metric to use for classifying when the localization has worked correctly is something called Jacquard distance, or intersection over union. And that basically measures how closely two sets overlap, and if you do it for polygons, how closely those polygons overlap. And this is a really interesting one, because as a metric, it really heavily penalizes inaccuracy. So sometimes you might see something that a computer, an intersection over union that a computer has done, and you might say, well, that's a really amazing polygon that it's drawn around that, the piece of cake in that image, and yet it'll have a really bad intersection over union score because of the dithering around the edges of the polygons, and that's kind of quite heavily penalized. So it's kind of an interesting metric, because even a 60% intersection over union can look quite good to a human. Whereas in the other ones you need to like 95% for them to be like a considered human scale quality of drawing. So how do we get this? And I'll do intro to kind of neural networks in a way that hopefully will be understandable. So if you think about the inherent logic through all of this presentation is that images are ultimately numbers underneath. Red, green, and blue values, or black and white in this case. Those pixel intensities convey information that we can then use to try and figure out what is in the image. So I'm going to go into neural networks, and then I'll discuss kind of types of neural networks later. So if you imagine passing every pixel value kind of just like linearly through a series of weighted equations, and then passing it through what we call an activation function, which effectively just imagine if something's if the weight takes you over a certain value, it might trigger the activation function, or if the weight takes you over, it might do it smoothly, or it might do it like non-linearly. To think about that in more simple terms, what you're really doing is effectively the weights, initially usually they're pre-randomized, and then you kind of have a process that tries to guess the weights. You add a beta on the term, and just to is like, kind of like a slack variable, I guess you could call it. So it's usually done best kind of via an example. So if you imagine, and this is kind of just from the TensorFlow example. So there's the good stuff. The good thing with all of this, the stuff I'm doing here, is there's loads of material online for it. There's loads of material from Google and Facebook and academic research papers. And this is literally the kind of TensorFlow 101 basic example of how to learn a neural network. If we were trying to predict 3 class labels of just 7, 8, or 9, we ultimately want the probability to look basically to trigger and trigger for the class 8, so it gets the label of 8 correct. We measure accuracy in this case via a metric called cross entropy. This function is really important depending on the type of problem you're trying to solve. Cross entropy is like quite a good place to start, but there's more you can do with it if you're solving different kinds of problem. But we'll stick with that. So we basically, what we're saying is we're comparing a labeled accuracy, which is our ground truth, with what the network thinks the label should be. So we say, in this case, the network says you've got 0.9 for class 2, and the ground truth is it's actually 1 for class 2. And we want a way of kind of basically doing that class of the machine learning, i.e. we want a way of kind of the machine to try and improve its accuracy of predicting class 8. So what you do is you effectively run a series of iterations, which is generally known as epochs, to try and improve that accuracy metric. And so when people talk about like this, the machine learning of a neural network, in my head, this is kind of the main step of that learning, where effectively every time you're trying to improve your error loss or decrease your error score, and therefore it's kind of improving itself and improving its model as it goes along. So that series of weights, if you look online, often you can actually download that series of weights, and those are literally just numbers that initially started as random, and via this process of scoring the accuracy and then trying to optimize that loss, have become more and more accurate at predicting the classes. And the weights are usually quite sizable in terms of how, like their megabytes or gigabytes that they take up. Just because they're, if you imagine this is 2 layers, you can add more and more layers, and what ends up happening is you end up kind of being able to identify more and more higher level features. Usually, the deeper your network goes. So whilst initially you might have simple patterns, eventually you end up with eyes, eventually you end up with faces, eventually you end up with scenes and landscapes and everything else. And just sometimes these things are the initial step there. They're similar to Gabian filters, or they are Gabian filters, which are kind of the rods and cones. The reason this is interesting is because some of the basic pattern detection your brain does uses Gabian filters, which are kind of these very straightforward, kind of like gradient fill type. If you imagine the kind of PowerPoint background gradient fill things, where you've kind of got like a circle with radiating different colors, or like a diagonal line with one color on the side in different gradients, that's kind of analogous to what a Gabian filter is. And you can combine different Gabian filters to end up with more and more complex patterns. From there, so that you can actually recognize multiple classes within an image, and to make the processing and kind of transformations more easy, there's this convolution step, which is literally the process of just kind of jumping around the image to try and find, to basically only pass through smaller sections of it. The interesting thing with convolutional neural networks is they initially, there's a guy called Jan LeCun who kind of wrote the initial paper on them, and he initially they weren't used, they weren't kind of seized upon straight away, but there have been various kind of competitions to try and improve the performance of image classification tasks, and these have kind of just come out as the model of choice for those problems. So you do it for every tie, and you output, and then effectively you just kind of keep doing more and more layers of the neural network. So the thing with neural networks, and this is kind of one of the astonishing thing that me and my team found when we were learning them, is you can kind of keep going deeper and deeper in your understanding of them. So you can keep learning more about different network architectures that solve different problems better. You can keep kind of changing and tweaking settings to try and improve performance. And it's definitely at the point where if you read kind of the literature, I think it's definitely more kind of art than science in terms of how people are choosing the network architectures, because it kind of just often it feels like someone's taken a punt on a different approach, and that approach has worked miraculously for a certain type of problem, rather than, because the computation takes so much effort, it definitely feels like people aren't necessarily doing so many kind of comparisons of different models when they're writing their papers. You get that kind of comparison when the big competitions run, or when people publish different types of model. There's a ranking of accuracy and other stuff, and other kind of metrics. But on a kind of paper by paper basis, it very much seems as people are just like really creatively trying different ways of improving their performance for very specific different problems. So one of the things you can do is change the network architecture. So initially we talked about a one-layer network. We've added, and then we moved on to a 3-layer network. Well, people have kind of gone crazy with it and just gone to like 20, 30 layer deep networks with all sorts of different functions on them. The UNet one is interesting because this is, if you see, it's kind of unbalanced. One step goes kind of straight to the end, as it were, and then you've got these other steps that kind of go deeper and then back up. That's really, really good for the image segmentation problems. So if you look at, for example, if you're a map provider and you want to trace over maps, so say where's the grass, where are the roads, where are the water, if you look at the latest Kaggle competitions, it'll be UNets that generally, or UNet-like architectures that win those problems. So for instance segmentation problems, they're really good. The problem is they're very slow to run. Like they're not real times. They're not able to solve real-time problems or do it quickly enough to be semi-real time. The one that's really cool and was kind of the Daniel Craig James Bond example I gave was YOLO, which stands for You Only Look Once, and is a really cool model that's all fully open source. You can even download pre-trained versions of the model. It runs really fast, and it can do 9,000 different classes of objects in 60 frames a second, which when it at about 78% accuracy. And what that means is it pretty much runs faster than your eye can see stuff, which is pretty crazy when you see it working fast. There's YouTube videos and lots of demos of it online as well, which I'd encourage you to go and look at because it's kind of crazy. Now, there's one other piece of thing you can do with the network architecture, and this has kind of been around for a while, but it's quite new in terms of people applying it, which is called like define by run neural networks. So if you imagine the define and run is what the vast majority of neural nets are, and that's where you effectively spell out what the network looks like, and then you just say iterate over it, just do more of that. Define by run basically kind of allows the computer to just change the network as it goes, dependent on set criteria. So you might have effectively different layers drop out or different things change as time goes on. The define by run is very interesting because it solves NLP problems quite well. A lot of the new natural language processing approaches that use CNNs will use a define by run network. That's usually more the case than, say, some of the image recognition problems, which is quite interesting. So clearly there's something about define by run that makes them more performant generally at NLP problems on an accuracy basis. And then there's tons more stuff. So you can modify the activation functions. So those activation functions, they're really important. They kind of basically just act to speed up the learning rate by effectively making a decision when the weights happen. So effectively, they act to basically just speed up the process of the weights and the learning algorithm happening. A lot of networks, there's like sigmoid is really popular, like rectified linear units are really popular. And often these are various different activation functions will be combined in the same network at different points, because they have kind of various advantages at different stages of the kind of features you're trying to do. So sometimes, imagine you're doing the face example, sometimes you might say if you're trying to detect an eye, you might want, say, a sigmoid, which has like a really smooth curve. If you're trying to say whether somebody is the same person or not, maybe you want like a rectified linear unit one because it's going to make a very non-linear decision. You can change your learning rates. If you imagine the kind of if that saddle graph, the colorful one, as effectively like the optimal solutions, you can like alter your learning rate to get to a roughly accurate solution much quicker, for example. Max pooling is probably the most important other step you need to know, which is basically the process of just summing up pixels, and it's a way of really speeding up the processing time. All of this stuff is like a real trade-off between accuracy and performance, and max pooling and pooling of any form is like effectively a performance improvement method. Yeah. Other things to do with like early stopping if it's clearly looking like an unsatisfactory learning approach. bagging for effectively just trying to summarize results quickly. Again, these are all methods of performance tuning. Some of them have accuracy trade-offs, but those trade-offs are usually deemed to be worth it. And then dropout. So this is one of the things that that defined by run neural network does really well. Effectively being able to customize your dropouts, so kind of just not running stuff by certain neurons, it can substantially improve performance over the long term, because you're basically just having to do less graph traversals. And defined by run is, if you imagine, then you don't usually want to be too static with which things you choose to drop out from your network. So I think this is why it works better this is kind of my hypothesis for why defined by run networks work better for NLP problems, because effectively you're allowing the kind of graph to adapt for many different types of solutions. Whereas in image recognition, you're going to see like similar patterns. I've probably not explained that super well, but dropouts are super useful, I think, as well to do in most networks. So a quick example of training a net would be, there's a great library called TF-Learn for learning TensorFlow. TensorFlow is Google's library for doing image recognition, or specifically tensor calculations, but it's like predominantly used for a lot and most of their models. You can import TensorFlow Learn. The key part is to have a set of images and then a set of labels. So all the data sets that you'll get for this kind of problem will have a set of images, and sometimes for the segmentation ones you'll have a label and some coordinates for where the polygons are for when you're drawing around stuff in an image. And maybe you'll have like a separate another data set, so you might have an X, Y, and Z, but in general you'll have like X and Y classes for images and labels. You import those, you do a little bit of pre-processing. That bottom section there, the network building, is basically where you define that network design. You're basically just defining inputs and outputs, and defining what kind of operation you're trying to run. And then eventually you train a really simplistic model that classifies, and this is just designed to run this one I've example here is designed to run really quickly. It's not intended to be accurate. But effectively all you've got is, you input your libraries, you input your data sets, you do some image pre-processing. There's some really important stuff about like color correction. So images can be shot in various different lighting conditions, and so normalizing for those lighting conditions can be really important. And then one of the things that can be quite useful is to say add a bit of randomization to your training data within certain bounds, and that allows you to effectively kind of just have a more diverse training set for your when you actually plug it through a model. That data augmentation piece is the focus of like a lot of work and research, because it's quite interesting, the fact that you can like add noise and it still kind of helps out the network. The data augmentation part is also the source of some of the really interesting work that I think I'll talk about at the end about what's next. And then you just run the network, right? You just trigger it, set it off, and let it go. So if we focus back, just and I've covered these kind of in my conversation, it's like the first three problems are actually I'd argue like a pretty decent state from like a timeliness and accuracy point of view. There is a lot of work that can still be done to get the accuracy up to human levels, but they're relatively fast. The segmentation problem is just slow, and kind of it seems like there's a lot of work to do in that area. And it's generally reserved to some processes that can be offline, like drawing around maps or post-event analysis, for example. So the problem is this. One of the real advantages with the field is that authors share their neural networks, and one of the real trends is someone will share the paper, they'll share the data, and they'll share pre-trained models. So you can kind of enter into the process at any step you want, right? You can enter it into the theoretical step, you can enter it at the trying to train your own model on their data, or you can enter it at they've already built a model that you can go and reuse immediately for whatever you want. And that last step is actually something that we find really advantageous, because if you want to, so it basically required no work to get to the image or the solution on the right. So all of that previous work that would take a lot of time, because somebody's pre-trained the network and given you those weights and the classes, you can get to the results really quickly. Usually they're published under pretty generous licenses. either like fully open. This is what this one is done with, I think, basically a license that says do whatever you want with it. Some of them are published under like MIT or various other kinds of pretty generous licenses. And then this is another one, like why don't you train your own model? There's a guy in Israel called Tal Hassner who takes that same approach of paper, code, data, and pre-trained models. So he literally even releases his code for you to use, usually for research. But they released something which estimates gender accurately, like 86% of the time. That's a pretty incredible accuracy for having to do effectively no work, from scratch. And the same for age as well. Age is a little bit worse, but it's still pretty incredible, I think, that you can go online and procure and get these things really easily, like free and openly, and contribute back to the research as well. So, for example, when we were doing this project, I found a bug in one of the TensorFlow implementation of YOLO, and I raised a pull request, and it got just merged within an hour into the library by people, because that's kind of how collaborative the image recognition community is, and how receptive they were to certain types of fixes and improvements. So in terms of what's next, I think this is all stuff that came out about within the last 3 months. The one on the top left is by a student called Carl Vondrich. I think he's a PhD or postdoc at MIT. And it's all about predicting what the future of, and generating what the future of image sequence might look like. So in this scenario, the green frames are effectively what the computer sees, and the red frames are what the computer generates. And so you can see, it kind of gets trained with that initial, just somebody kind of going to throw a basketball, but sort of going through a baseball, but it doesn't know what happens next. Their approach is actually on the kind of top left image. That's actually their prediction. So the red is all predicted and generated from that initial set of images. The previous best approach is in the middle, and then a very kind of basic optical flow, which is just kind of taking the vectors that were from the underlying video and kind of just playing them out into the future. So LSTMs are really popular for image sequences and pattern detection and pattern classification, and their approach achieves kind of this unbelievably freaky superhuman way of generating and predicting images into the future. The reason I really like that paper is because they take a really novel approach to data collection. So they basically downloaded lots of YouTube videos that were all unlabeled, and they ran them through the kind of most accurate image classifiers, and then they used that to train up their sequence classifier. And so I really like it because it's a really novel approach to kind of the problem of not having enough data, and kind of a bit meta as to kind of using a image recognizer to train up a sequence classifier. And the results are super impressive. And he's a really great person to follow on Twitter. His name's Carl Vondrich. He's always tweeting it's like 100% quality. It's really nice to just to get you see this thing pop through and you're like, that's awesome to read and follow. The deep aligned representations, I think, is also one of his works, where they've basically proven that by a specific unit within the neural network is activated for when it receives, say, the sound of a swimming pool, an image of a swimming pool, or the text describing a swimming pool, which, if you think about the kind of generalized learning stuff, is quite a major advancement, because it means that effectively it has reached the network has generalized enough to know that it has this abstract concept of a swimming pool, which is triggered by different types of data. So that's kind of like one of those things where you could imagine, layering in, say, more movement data from a robot, and maybe eventually you might end up with it knowing what swimming feels like, for example, as the same hidden unit. I'm using in anthropomorphic terms, which probably doesn't help, but the same unit would be activated for, say, swimming and swimming pool or that kind of stuff. So it's kind of like a more generalized version of the network. The dexterity network is super cool again on the image, but on the data collection side of stuff. So this is from researchers at Berkeley. They generated 3D shapes that basically never existed, or they basically just made 3D models. I think they made about 6.7 million 3D models. and then they trained this network to try and optimize the grips that it would take, i.e. if you had a robotic arm, it optimized like how it would grip the objects. But it did that without ever knowing the physical world. It did it only on the 3D generated objects. And when they trained it on 1,000 unseen object types in the real world, it had like 99% accuracy for picking up objects. So it basically only dropped like I think one object, because it always figured out the optimum pose with which to pick up the objects. And I love that approach again of just like, it's not like the YouTube approach of using a classifier, but it's still being really creative with the data generation and the data collection approach. Some of the kind of original researchers on neural nets have made a lot of done a lot of work on kind of the the understandability of neural nets, which is that bottom left-hand one. So just trying to figure out what it has learned as a representation, or what it has abstracted as a representation of an object. So when people talk about that kind of, I think, or whenever some people talk about like, what has it learned, and we need to understand it more, like we don't want it to be a black box. That's one of the papers that's really gone down that route from a very technical angle. And then this other one is something that literally came out like a few in the last week, which is it's kind of absurd, where it basically takes a 2D image of an object and tries to give you a 3D reconstruction of what it is. So on the surface of it, it seems kind of very straightforward, but if you think about it, it has to have learned like how a 2D shape and a 3D shape, effectively like what the kind of mapping might be between them, and therefore be able to kind of do the transformation accurately from a 2D picture of a chair to a roughly 3D model of that chair. And there's even more examples of it, and it's not just types. It's like types of chair. It's not just a chair and a car. It's like types of different car, like a pickup or an estate car, or types of aeroplane, like a big aeroplane or a prop or something smaller. So these are all kind of these insights into the research that's going on, and kind of little insights into, you can imagine the dexterity network on a production line or picking. You can imagine the generating the future. The generating the future one's really funny because it's like it's done like sliding doors. So they make the example that the future is inherently uncertain. So they do some really clever stuff about actually picking the most certain future versions of situations. So it's not just picking the average future scenario. It's picking it's saying, well, there's like 3 or 4 or however many different scenarios that could play out, and then trying to give you the most probable scenario from that image. But then one of the things I was asked by a client that I was working on was basically for like Minority Report-esque, can you predict the future of, can you predict when there are going to be accidents like in a retail environment, like a slippage or basically a health and safety type incident. And so I was like, that's a really hard problem. I'll go away and research it. And the very best you're going to get is kind of a rough generated version of the future about a second in advance. Or unless you take a different approach, but again, the accuracy falls off so quickly that it's just not there yet.